together using strictly public data. So all the data here is from either the USGS or S&P Capital, but it's all data that you can download from the website. And later today or tomorrow morning, I will be uploading this presentation to Jeff Hedquist's science, his FTP, so Science Direct. It will be available. Jeff and I are very active members of the SEG, the Society of Economic Geologists, which publishes Economic Geology Journal. It holds conferences yearly, and we also have a series of funds that students, early career geologists, and even advanced career geologists can apply to get further advancement in their careers. Here's the map of emerging Asia. Emerging Asia makes up about 16% of the world's explorable landmass. There are about 40 countries. It does not include China and Russia, because those are countries that are considered to be beyond the financially or economically emerging stage. And this area is so large, it encompasses a variety of mineral deposit types that were formed in all possible tectonic environments, all metal associations. So it's a very tough thing to summarize this into a 30-minute capsule, but here's our best attempt. This is the map that we're going to be looking at for the rest of this master class. And I'm going to remove the country names, but I will keep the international boundaries to give you context of where things are shown. In emerging Asia, we have some very old, stable cratonic blocks shown here in pink, like the Indian Craton, the Arabian Shield, Yangtze. These are blocks of crust, of continental crust that hasn't seen much deformation at all since Proterozoic times. And India is a very good example, because India came from the south and collided against Eurasia. And the collision, the result of the collision, is all of the Tibetan plateau and the Himalayas. And here in the previous one, we saw the subduction happening beneath what is now the Himalayas. And what is now the Himalayas and the Tibetan Plateau, these are the evidence of that collision, this highland. And that collision, that evidence, we called it a suture zone. And I'm going to be using that word, back and forth, suture, because the suture zones tend to focus mineralization all around the world, but we want to focus on them in emerging Asia. Then in between the stable continental blocks, there are a series of magmatic arcs. These are volcanic arcs, some of them still active. The yellow ones are Cenozoic, we are still in the Cenozoic. So these volcanic arcs, they young towards the south, and towards the south they are still active ones. So now let's have a very quick overview of the tectonic settings where the deposits, the different types of mineral deposits form. First, let's look at the rift setting, where the crust is being extended, pulled apart, and forms these domino-shaped fault-bound blocks, along which there are sedimentary-hosted base metal deposits, there are volcanogenic polymetallic deposits, and further deep beneath those extending dominoes, there are layered complex nickel-copper PGE deposits, as well as alkalic carbonatite rare earth deposits that form. And a further stage of extension of the crust, we now start forming new crust, oceanic crust, in a spreading ridge. Let's see if I can point. I don't think it would point, but there's a spreading ridge there where those two arrows are diverging, and continent lengthwise from the spreading ridge on the edges of the continents, we get sediment-hosted copper, lead, zinc deposits, very rich ones. And if that tectonic polarity is inverted, or when it is inverted, and those two continents start moving towards each other, then we start subducting that oceanic crust. So here we see the subduction, and above the subduction, volcanic island arcs and porphyry deposits forming, both in the island arcs and in the continent. And above the subduction zones, we also form orogenic mold deposits. And associated with the porphyry deposits, we have a clan of other deposit types, epithermal, skarn, IOCGs, all related to them. And finally, in the collision stage, where those two continents, or those two crustal blocks already came together, we get the orogenic deposits above the suture, right above what was the subduction zone. We get lithium, tin, tungsten, rhyzins, pegmatites, porphyry, copper, moly, gold. And farther inland, because of that subduction happening, there's traction in that subducting plate that will actually produce extension in the back arc, or back arc basin, which is extension. And there we formed the stratiform copper, the deposits, the Mississippi Valley type sediment-hosted base metals and copper deposits. And here is a map of the major tectonic units of emerging Asia. At north, we have the Central Asian orogenic belt, or also we prefer to call it the Central Asian orogenic supercollage. This is a term that Yakubchak uses, Sasha Yakubchak, many of you know. We have in yellow the Tethyan belt, which is the closure of the Tethyan Ocean, and in pink, those stable continental crusts, and in blue on the side, this is the tectonic domain associated with subduction of the Pacific, of various Pacific subplates, and not the Tethyan. And in that Southeastern Asia part there, this is where things get really complex, because Tethyan is still subducting, and the Pacific is subducting, and the interaction between them is making some very complex geology, very complex structural geology, complex geometries, and very rich mineral deposits. Now back to the sutures. Here are the sutures. Let's compare the suture zones of the Tethyan, that yellow zone. The Tethyan sutures, as we know them, they're fairly linear. Yes, there are some kinks, for instance, where the Pamir and Denter happen. There are some kinks, but in general, they're very continuous and linear. Whereas in the Central Asian orogenic supercollage, our sutures here, they're much more warped, folded, kinked, hinged. They're much more complex than the Tethyan ones. And this is not only because these are older rocks in the Central Asian orogenic supercollage and they had more time to fold. These folds happened while these sutures were forming, while the arcs were active. So it's really a very different tectonic environment. The arcs, the Tethyan arcs are very different from the Central Asian supercollage arcs. And that, speaking of arcs, that takes us to the porphyry. So once again, I'll reiterate that all of the data here is public. All these polygons with the magmatic arcs, this is all from the USGS. You can download this data from their website in GIS format. And the stars, they depict mineral deposits and important occurrences. Those two are from the S&P Capital database of deposits with resources. and from the USGS. And what we see is the porphyries line up fairly well along the sutures on the Tethyan all the way from Turkey, and it takes some kinks around the central Anatolian block. It takes some kinks here in the Pamirs, but it goes smoothly down, straight down Iran, goes into the Pamirs. It takes a big kink, disappears in the Himalayas. Most likely for political reasons. We know that there is good potential for porphyries there. And then they show up again in Southeast Asia as a very continuous part of the Tethyan belt. And then if we look at our part of the world in the Central Asian orogenic supercollage farther north, the porphyries there, they still follow the sutures, but the sutures are much more convoluted. They are folded into hairpin folds and warped, but they still control the locations of these deposits. And for those who like some numbers, like to see some numbers, these are exciting numbers, particularly for us, because here in our neighborhood, the Al-Malik really throws everything else out of proportion. Really, the Al-Malik porphyry in Uzbekistan is by far the largest of all of them. And I want to now draw your attention to Southeast Asia, to the Indonesia part down here. This is Indonesia, the island arc, the currently active Tethyan island arc. Tethyan Ocean is still subducting underneath Indonesia, still subducting underneath parts of Iran. And here we have, just from the topography, we can see the volcanic edifices, the volcanoes, and we can see their craters just on the topography, right? The brown area is the highest topography. Here is some volcanics like Bromo, Gen, Merapi. There are some active geothermal sites with very low pH. And if I'm not mistaken, this guy on the photo on the right is carrying a basket of lava. I don't know why. This is Jeff Hediquist's photo, but that's what it looks like, right? So here is the axis in white, the axis of the active volcanic belt. So these are the currently active volcanoes. Now, if we focus a little bit farther to the south, there is another axis of the Miocene volcanics. Miocene is 25 million to around 5 million years ago. Those are much more eroded. They're lower lying volcanoes. They're no longer active volcanoes, but those are the ones that are fully mineralized. The active ones, they have deposits in the making. There are porphyry and epithermal deposits that are forming in them. But in the Miocene deposits, they are already, not only already formed, but the topography has already been eroded to the level that exposes them on surface. And so here are some of the deposits with their sizes in black. And in white, the white circles are the prospects or exploration properties without resources. And the red circles are lithocaps. These are alteration assemblages that are known to occur above porphyries. And what I want to bring to your attention here is how the periodicity, the repetivity, the repetition of these, periodical repetition of these, both in the active volcano axis along the active volcanoes, and to the south of them, in the shade of the active volcanoes, practically one-to-one, we have either a deposit or an exploration or a lithocap, an exploration project or a lithocap. And now what I want you to think in your mind, translate this into the Central Asian orogenic supercollage. We have the same, we see the same if we're exploring in Malhash, except it's not a linear belt anymore. It's hinged and folded and warped and very convoluted, but the periodicity is there to be uncovered, to be unraveled. And associated with porphyries, there are, am I going the wrong way? Epithermal deposits. some of the large epithermal golds are in, once again, South Pacific is very rich. But up here in the Central Asian orogenic belt, we have some very rich deposits as well. And we also have a series of other types of gold deposits. So starting with the VMS, the volcanogenic massive sulfide, in which gold is not a primary commodity, yet it can make some pretty rich deposits, like our reader here. And in blue, so those are the ones in green, the volcanogenic massive sulfides. In blue, these are sediment-hosted gold, similar to the Carlin deposits in Nevada. And an interesting one is that belt that goes from southern Kazakhstan into Kyrgyzstan. It's seen a little bit of exploration, not a whole lot. It's a very exciting belt. For political reasons, it's been stalled in Kyrgyzstan. And then we have in red, the red polygons are the orogenic gold belt. And those are really from the gold deposits, from our perspective here in Central Asia, those are the most exciting ones. And I want to bring to your attention the area in that yellow polygon there, which is the Tian Shan Mountains, or the Tian Shan belt of Central Asia. The Tian Shan can be divided into 3 geological subunits, with the southern one, the one in magenta, being the highest elevations, the most deformed, the most complex structural geology, very difficult to understand in the field, but also the best endowed in gold. It's the richest one. It hosts the giant, the Kuntor, the Munutao, and besides Munutao, it hosts a variety of deposits between 500,000 and almost 9 million ounces of gold that we consider small in comparison to Munutao, pale in the shade of Munutao. Now, an interesting thing about the Tian Shan is it's an arcuate east-west trending belt, all the way to the border between Uzbekistan and Kyrgyzstan, and there it starts jogging towards the south, towards the northwest, jogging and horse-tailing, so it splits into separate branches. The technical terminology in structural geology for that geometry is horse-tailing. And each one of those horsetails, for instance, the one that hosts the Potash, a bit farther to the west of the known deposits, they disappear under the cover of the Aral Sea sediments and consolidated sediments. And these are belts that haven't seen the modern undercover exploration techniques that were developed for thick pediment covers in Nevada and Australia. So some of it has been done, but not as extensively as we've done, and as extensively and as much with much success that we've had in Australia and in Nevada in the Carlin Trend. And now we go on to sedimentary copper, which is another one that is very interesting for us here, very close to home. The biggest basins are the Shusarisu in southern, south and central Kazakhstan, and the Chengiz Basin farther north. Those are the ones that have, you see a lot of red dots there. These are the deposits listed in the public databases. But there are other areas in Kazakhstan. For instance, there are a series of smaller tracts just to the east of the Chengiz Basin that have the same rocks of the same age, the same pathology, hosting the same type of mineralization, but because they're not a very well-preserved basin, instead they are fold and thrust belts, they just haven't received as much attention. They're starting to get attention, but there are areas that have very high potential for sedimentary copper. And in sedimentary copper, of course, we have the giant Kazgan, and just outboard of the sedimentary hosted copper basins, we have the SEDEX deposits, some large ones like Jarem, But when we talk about sediment-hosted, SEDEX and MVT, sediment-hosted lead zinc deposits, the Mediabad in Iran takes everything else out of proportion, out of the competition, right? It really is the largest of all. And interestingly, whereas most of those sediment-hosted deposits are in the tectonic units of the Tethyan and the Central Asian orogenic supercollage, there is also an important belt in India in the cratonic rocks. And now we go on to a very brief overlook on critical raw materials, starting with polychromite and nickel, copper, zinc. Indonesia and the Philippines here in Southeast Asia are the big producers, right? If we're interested in a deposit, that's the place to be. But we can also see that if we follow along the suture zones, both in the Tethyan domain and in the Central Asian orogenic supercollage, we see that there are nickel, copper, PGE deposits that mimic those suture zones. Now, at first, this may be counterintuitive, because if you remember the slide of the tectonic setting of these deposits, they form in an extending crust, or at the base of an extending crust. So why do we have these deposits following along the suture zones, which are compression? What happens in the compression is above the subduction zone, there are pieces of the crust, of the lower crust, that gets abducted and regurgitated farther up to what are now mineable levels. So what used to be an extensional environment now got trapped in that subduction abduction, and gets exposed along the suture zones. So suture zones are a great place to be looking for everything. And out of the suture zones, one of definitely my favorite and many people's favorite is the Urals. The Ural belt is a north-south trending belt. It makes up about 2% of the Russian landmass, but it also makes up about 25% of Russia's metal production. So it's a very rich belt. North-south trending, it's been mined since the Bronze Age. Everything is north-south with some kinks, but it's all north-south. But when it gets into Kazakhstan, in northern Kazakhstan, it disappears along this east-west end, which is strictly imaginary. There's nothing east-west there. What it is we don't know where it goes from there. It goes under the cover of the Aral Lake sediments, similarly to the Tian Shan Mountains. And somewhere beneath that area, somewhere beneath the Aral sediments, the Ural Mountains and the Tian Shan, the Ural chain and the Tian Shan chain intersect, and that's got to be the richest intersection for metals. We don't know how deep it is, we don't know if it's explorable or not, but that, in my mind, that is the richest portion of Central Asian orogenic supercollage. Rare earth elements, we have pegmatites, mainly in the shields, right? So the Indian shield, but in the Tethyan, there are also some rare pegmatites. Vietnam, Thailand, and Myanmar are the main producers in the Tethyan. But we also have in Vietnam a belt here of some pretty important deposits, which are the southern extension of the Tethyan Chinese pegmatites, rare earth pegmatites. Lithium, when we look at emerging Asia, it doesn't make for a very exciting map of lithium other than the Iranian recent discovery of 8 gigatons. And part of this is because the exploration for lithium really picked up in the last few years. And as I said a couple times, and I mentioned, bring it up again, this is strictly based on public data sets. And this huge exploration effort that has picked up in the last few years hasn't had enough years to convert excellent exploration targets into resources. So we have to really understand the lithium scene, we have to look well beyond the public databases. And we start seeing, well, there's a Canadian company that recovers lithium north of the Caspian Sea. They intersected lithium brine in one of their oil wells, a junior exploration company. There are companies here that are exploring all of the Kalba belt for pegmatite-hosted lithium. So there's quite a bit there. It just hasn't matured enough into the public databases as records that hold resources. So to conclude, I've shown you this incredible complexity of particularly in the Central Asian orogenic belt, but throughout emerging Asia. And it's a complexity that scares many. Structurally, it's a very complex area, geologically very complex. But in spite of this complexity, what I want to show you now is that there is great merit in exploring here. This is an excellent area to be exploring. So let's take copper as a thermometer to show you why this is an interesting area to explore. If we look at the current deposits, all the known deposits, this is compiled by the USGS, a majority of more than half of the deposits are in the Americas, and South America is the place to be, right? So blues, South America, North America, and Asia doesn't have a very impressive profile there. But if we compare that to the undiscovered deposits, now Asia overtakes the Americas in terms of tons of copper. And what do I mean by undiscovered deposits? This is not my hallucination or dream. This is from the assessment of undiscovered copper resources, worldwide assessment of undiscovered copper resources by the United States Geological Survey. To make these assessments, I'm quite familiar with this methodology because I used to do this in the Canadian government. They employ people from the industry, high-profile people from the mineral industry, and they're scientists and scientists from academia, and together they come to the results of these assessments. And here's the map showing the overall results of undiscovered deposits. The huge ones, are still in South America and surprisingly some in Mongolia. But it's not surprising that Mongolia has potential for huge ones. What's surprising is that it's in northern Mongolia rather than in southern Mongolia where the Oyo Tolgoi is. That came out as a surprise. But we also see some hot tracks over by the Uzbekistan-Kazakhstan border. But the interesting thing to see is if we look at this map and ask ourselves, where is there most color? Where is it most colorful? And this is actually here where we are, right? Central Asia is the most colorful. So according to the USGS assessment, we don't have huge deposits everywhere. We do have some belts of huge deposits, but we have a huge amount of copper here in Central Asia. And here we go back to our map, and just to put it back into the map that we were looking all along, we have some the hot red areas are the highest, the deposits that are considered the undiscovered deposits that are assumed to be the biggest one, the largest tonnage ones. And of course, we have a few of them right along our border with Uzbekistan, and by Kazgan, of course, here in Kazakhstan. So with this, I invite you to explore in this area. This is a very exciting area to explore. And I invite you to find more information about the Society of Economic Geologists, where I hold a volunteer position as the VP Regional Affairs for this region here, for what was called, until recently, Northern Eurasia. We're renaming it Central Eurasia. for obvious reasons. But with these QR codes, you'll find information about the SEG, particularly for students. This is there are great opportunities for getting field trips paid, for getting professors coming in from other countries. There are a wide variety of possibilities. And catch me if you want any more information. And once again, I will be uploading this to Jeff Hedequist's science director. I can't think of the name right now, but it will be online. You will be able to download it. Thank you very much for your attention.